Okay, so welcome everyone to the 10th edition of the Quantum AI monthly series. We have today very distinguished speakers. They are going to address several and different topics related to quantum AI and the quantum technologies, and also a reflection on the year of quantum, the year 2025. And also are going to end up with a roundtable to address fundamental questions related to the quantum advantage, what is expected from quantum computers, and what the future look like for quantum computing in general. Today I have my colleague, Engineer Youssef Eldakar. He's the head of International School of Information Sciences at Bibliotheca Alexandrina, and he's gonna present overview about the activities that has been done during the year. And myself, we both organize this monthly series. The monthly series was quite successful for the past year. We had about 10 editions so far. We started exactly on the 19th of December last year. And as Yusuf was saying, we are having a soft end with the same day, like on December 18th today. We started with topics from quantum computing applications in chemistry and the simulations. This was in the launch of the series. And then in February, we continued with introduction to quantum computing and the quantum computing for chemistry, plus quantum encryption. And we have discussed quantum modeling, quantum AI agents with very distinguished speakers from all over the world. Then quantum machine learning and also classical machine learning as well, quantum machine learning and optimization and IBM quantum use cases, quantum education and the technologies and the research, quantum communications, encryption, and what we mean by a Q-day, also molecular dynamics, quantum simulations and advanced quantum algorithms, quantum machine learning and the quantum sensing and the benchmarking. And today we have our last edition for this year, the quantum AI progress, quantum energy consumption, and of course, neuro-linguistic programming with quantum AI. So now with this, I'm giving the floor for a few minutes for Engineer Youssef Eldakar to highlight and reflect on the different activities that has been done during the past year.
Thank you very much, Dr. Taha, and welcome everyone once again. Let me share a few slides. Yes, welcome everyone once again. This is a collaboration between the Bibliotheca Alexandrina, the Library of Alexandria, and iQafé. And of course, everyone in the community has been helping very much during the past year. It's really nice, like my good friend just mentioned, that we are the first edition of this monthly series was on December 19th, and today is December 18th. So it has been a year to the day. So let's maybe look at some of the things that happened over this past year. We started with this monthly series as a way to build community and build capacity. And this was December 18th. And a few months after, there was the Quantum AI Lab, which gave space for people to practice hands-on. And many thanks to our wonderful mentors who have contributed a lot to this activity. So why we're doing this? Again, the general idea is to build capacity and build community. We want to stimulate the quantum ecosystem in the region to build space for students and researchers and computational researchers, and specifically in quantum computing, to learn and network. And we also look forward to always connecting this ecosystem with other ecosystems. And it's really nice that we see different people attending from different areas of the world. Eventually, we had the hackathon. That was in September at the Library of Alexandria in Alexandria, and many thanks to everyone who joined us there. But also many thanks to all the people who put effort into making this hackathon possible. Of course, our partners, but also the community, because let's remember that before the hackathon, many things took place. It wasn't just the 3 days when we got together at the library. We had, of course, the multi-series and the lab, but then closer to the hackathon, we had the summer school and also a dry run hackathon, which I think were two very significant activities that led to a successful event that we had. We had the hackathon. It was fun to get together and see, listen to the talks and see the teams work on problems and make progress and eventually present them. And eventually we had the winners, and that was really nice that we also had the opportunity for good networking, excellent networking, that I'm sure will lead to many good things beyond that. And now we're planning for a hackathon, inshallah, in 2026. So we have our main activity, the multi-series, accompanied by the lab, but also our good colleagues in the community launched a new series, the Ask Quantum Industry series, which is, I guess we can say it's a podcast-style series that gives the opportunity for interaction with the experts in the field, in the industry, and ask questions and learn more about what's happening. So we're really excited about this, and also always very, very happy to endorse this and support it at the Library of Alexandria. We had like we just were saying, we had a very nice collection of lectures full of interesting content, which, in my opinion, if we group this all together, we can make a nice book about quantum computing. Maybe it's an idea that we can explore. We had so far 9 editions, and this is the 10th. So we almost had we had 10 editions during the year, so that's really nice. We're going at a steady pace, and the lab is I think is a good way for people to get started, because in this field you always want to be able to get your hands dirty with the technology and practice and solve problems. We have currently 13 published labs, and the lab is offering 2 tracks: the quantum simulation track, but also the quantum machine learning track. We're looking forward to the Ask Quantum Industries series, the new series, to continue and feature diverse guests from different parts of the quantum ecosystem. A new idea that we are experimenting with, we called it the C Forum for Computational Forum, which is hopefully will be, we'll have a website published sometime soon at cforum.bibliotheca.org. The idea is to link different things that we do related to computational research, and of course, including quantum computing. We have different things happening on the scene. We have the HPC, high performance computing, which has been there for years, and it's a way for to support the university and the research with computational researchers. With computational resources, we have our activities in quantum, such as the multi-series, the lab, and the hackathon, which hopefully will be something that happens every year. sort of like a gathering for the community around the idea of quantum computing, which is something that that's really groundbreaking, obviously. And so we hope this this platform, this website, this Nexus will link the different things together and maybe offer also an opportunity for further tutorial type of sessions, more hands-on practice opportunities. We already have the summer internship program at the Bibliotheca Alexandrina, which is very active, has been active for several years. And looking at it and looking at the projects that come out of this program, a good number are related to computation research in a way. Some of them, we give them access on the HPC cluster. So again, it's something that maybe if we link all of that together, something wonderful will come out of that, and we'll be able to explore further opportunities. So it has been a good year, and at the end, just for a quick announcement, we have our good friends at the IEEE student chapter in Egypt. We together are organizing the hardware carnival, which will be hosted at the Library of Alexandria in just a week from today, on December 25th. And we're happy that iQafé will have a presence there as an opportunity for people to ask questions about quantum computing and learn more about this domain. So if you have any thoughts or questions about what we are doing and what we're looking forward to be doing, please get in touch. My good friend Taha and I will always be happy to read your messages and have a conversation. So thank you, everyone, and I'll hand it over to Dr. Taha again to continue with the program of this 10th edition of the monthly series. And I'm sure we're excited to listen to the talks by our good speakers. So thank you, everyone.
Yeah, thanks very much, Engineer Youssef, for the nice presentation, the nice overview. Indeed, it's a great pleasure and honor also for to be present in the carnival. And there is also opportunities which we are gonna hear about later on, especially from Dr. Damir about several activities, and Engineer Ahmed Salim, and as well related to education and research, and bridging the communities and the different ecosystems from the Arab and also North African region with US-based ecosystem and activities as well. So thanks very much again, and I'm gonna back to my slides, and I'm reminding people, if you have any question, please feel free to drop it to Engineer Youssef either on email or on LinkedIn or WhatsApp or any means that you find convenient to know more about this activity. Yeah. And now we are gonna start with our first speaker, Dr. Damir Kavar. Dr. Damir is an associate professor of quantum computing, quantum AI, and NLP at Indiana University, and he's gonna present optimizing data structures for hybrid classical and quantum computing for AI and NLP. Feel free also to visit his LinkedIn page for more information and more news about his research, and also the university page about his research work and research group as well. Okay, Dr. Damir, the floor is yours.
Thank you. Let me try to share actually can I present now? Just go here. This works like this. Okay, let's just do it this way before I experiment further. So this is just a modest summary about some of the activities that I did in my lab here that had to do with approaches in natural language processing and AI, where we were trying to figure out how good could we make classical and quantum computers interact by sharing models. And I will introduce a little bit about word embeddings and the vector models that we are using in natural language processing. And this is now applying also to all the modern state-of-the-art AI systems, from GPT over to Claude and Gemini and so on. And I'll discuss a little bit similarities and also analogy that we use to measure with vector representations of lexical items, of language meaning, semantics. I'll discuss a little bit the data set and the experiments that we ran, and then what we are working on right now. And feel free to sort of comment and give us suggestions. We are looking for any kind of ways to improve that and facilitate our research activities. So in natural language processing, the goals were basically to come up with neural models to apply sentiment analysis, text classification, speech and language processing in general at various levels. And while vector representations of words and text were very common actually in the 90s already, and later on, one of the big insights and innovations came with Word2Vec, a group at Google that basically came up with a strategy to use what they call distributional semantic properties and map word properties into vector spaces automatically, unsupervised or semi-supervised, and use those in downstream applications in neural models to train, make predictions about text, content, named entities, and various other aspects. This has been expanded by colleagues from Meta or Facebook back then. Fast Text was a model developed by them. Glove is a model that was later developed by Stanford that had very specific goals and ideas actually in the training of these vector representations of words and meaning. And I'll show you an example in a second. Number Batch was a group of colleagues at Northwestern that was working on ways to include semantic graphs, knowledge graphs, or ontological knowledge in such as a training base for training such embeddings and vectors. The big next step was basically the development of BERT, and I will talk a little bit more about that. This is what we are focusing on right now, that showed that in many derivatives and so on, with a very specific strategy and implementation using transformer models and deep transformer models layered, we can achieve superior downstream results in processing text and language in general. GPT and Claude are now, of course, models that use basically vectors. You can, if you use the API of OpenAI, or for Claude, Anthropic collaborates with Voyage AI, you can pull the vectors for words or text from their endpoint. And you see already that the OpenAI vectors are 3,000 dimensional, the Claude vectors are 1,000 dimensional, and those are 32-bit representations of floating point numbers. Why do we use vector models? Well, one reason for that is basically that in neural architectures, we have to have a fixed input for language, for text and words. And string processing is not an easy approach or method, or hadn't been successful in the past. So we had like specific length. We have to find in the architecture, specify sort of the weight matrices and details about the neural networks so that we can process these kind of representations. And this has been shown, I mean, this is showing to be superior in various ways. And we can combine that now by using not just vectors to represent language and text and words, but also images and any kind of other data streams, also spoken language, for example. And in the past, it started off, by handcrafting feature vectors for text and language. We use distributional vector representations. This is implemented since ever in search engines and so on, matching of texts and various applications that build on search. And then Dense vectors were basically the innovation with Word2Vec with a group from Google that allowed to encode semantic similarities between words and tokens and improved then downstream applications of neural models over text. And so with machine learned vectors, what we had usually as a problem is that we need large amounts of data, and it's very costly to train those models. And they are made available now in on various platforms. Hugging Face and so on provides access to such models, as well as OpenAI, Voyage AI, and various others. And it would be sort of wasteful to say that we ignore that and focus now purely on developing similar type of embedding structures just for quantum. And we wanted to see how well can we actually take these existing models and transfer them into a quantum machine in a simulator, as well as we used the IBM quantum hardware, and see how efficient we can apply this in text classification or lexical similarity comparison. When we look at these training models for such vectors, the one that we are focusing on is the closer test. This is masked language model like BERT, where, you know, it's similar to tasks that you will find when you do a foreign second language learning program. Students are asked to fill in the missing word in a gap. And in a similar way, we train neural models to fill in the missing word in these kind of gaps. And the large language models are right now GPT and so on are, of course, trained on predicting the next word given a specific sequence of words previously heard or read. And the way that the BERT model, for example, the masked language model has been trained is, in addition, that one other task, an additional task, was to make a prediction about the continuation with multiple sentences. So if you give the model a sentence like "the cat sat on the mats," the question was, is a continuation like "it was a sunny day" an appropriate or expected continuation of this sentence? And this way you can sort of train downstream predictions about contextual continuations of events or text classification in general and so on. I will not discuss these kind of things in detail, but one thing that is important is in these models up to BERT, including BERT, what was the basis for tokens was words and sometimes subword segments. So words were segmented into pseudomorphemes that were then taken to be tokens and trained in these models. In the current large language model architectures, that's no longer the case. The tokens, the base for tokens is byte pair encoded sequences of just bytes basically, and this is for various reasons, including architectural reasons, and to cope with the large amount of possible words in the huge internet text corpus. And from multiple languages, one has to sort of optimize that and reduce the number of possible tokens for modeling to 100,000 or maybe 200,000 in the newer models and so on. So the research questions for us were basically, can common NLP embedding vectors or models that encode semantic properties of words or text fragments be used in a quantum environment? And for quantum AI, quantum NLP, and what are the most optimal ways to encode word embeddings for a hybrid classical quantum environment? And the issues are, of course, we have to transfer vectors from a classical compute environment into the quantum world, and we might face potential loss of information when the embedding vectors are encoded, and this is what we have to measure then. This is the sort of nature of the experiments and the scientific approach here. And when we look at all these different models that we had, that we tested, fast text, glove, number batch, you see the different dimensionalities there and what the base was to train these vectors, how many words. GPT and Voyage AI have the largest vectors, and internally actually They are using even 12,000 dimensions or far more for various reasons. They have to encode positional information and all kinds of other segmental information, which sentence, a word, or token belongs to, and so on. Now, if we look at that, just a very short vector representation like fast text with 300 dimensions of reals, what we are talking about is 98,000 bits to encode this. And if we would expand that and want to sort of increase the precision of these vector representations, we would have to double that. And the measure between texts and words that were represented as vectors would be, for example, cosine similarity if those vectors are not normalized, as in GPT, for example, or just use the dot product as in Claude or Voyage AI-based vectors, because those are normalized vectors. And what you want to achieve is a vector space of semantics of word meanings that reflects not just similarities of words, because you would expect that similar words would be close together in space, like cat and dog and mouse and so on, versus stone and cloud and car should be distributed in different regions of the semantic space. You would also want to have an effect that is what Rommelhart and Abramson in the 70s already emphasized. You want to use these geometries for analogical reasoning. And what that means is basically you would want to say that the concept sir is to madam what hair is to X, and X would be then basically harass. And the idea here is use a parallel and use equidistance to compute the expected analogous term that you would want to see in the answer that you generate. So man to woman is like king to queen, almost parallel and almost equidistant, right? So this is basically one of the ideas in analogical reasoning, and we want to do semantics over that, right? One way to encode that in quantum is basically, there are multiple ways, but one way is to use amplitude or dense encoding, so that we can say that 2 to the power of n bits or scalars can be encoded to n qubits. The amplitude is basically the superposition of qubits, and squared amplitudes could be interpreted or should be interpreted as probabilities of finding the qubit in a very particular state, 0 or 1. And there's implementations, there are optimized implementations of these algorithms. In the past, people were arguing that the result of amplitude encoding would lead to exponentially large quantum circuits. Reality is that we can keep the quantum circuits linear to the depth or to the number of dimensions in the vector that we want to encode. So that's not very deep or problematic, basically, in general, for even existing quantum computers. So we can compress something like BERT vectors from the model that I will go a little bit in depth about later, or GPT vectors, 3,000 dimensions. We can encode them in 12 qubits straight away in the amplitude. And now basically what this encoding means is I take a vector and I take the dimensions and map them directly into alpha, beta, gamma, delta, and so on, into these amplitudes in a quantum state or quantum vector. And you see already that if we take real vectors and do that, we basically ignore the nature of these amplitudes, alpha and beta, for example, actually complex numbers. So we basically have the imaginary parts zeroed out, and we just transfer the real part into the dimension, into the amplitude. And what we did then so we did experiments at this level. We transferred vector representations from GPT and Claude and so on into quantum states, and then measured in simulators and on IBM hardware what the distance, the similarity is. The interpretation here is basically if two words are similar semantically, like cat and dog versus cat and car. Cat and car would be dissimilar. This should be reflected in the dot product, in the inner product between the vectors of these that represent these words, right? And so we can measure then basically whether the semantic properties are preserved that we measure in the classical environment after, and then in the quantum environment after the encoding in say amplitudes. The results were already back then quite shocking to us because the loss was minimal. We basically achieved something like 0.9 correlation coefficient over just comparing over n word pairs the similarity scores from classical and quantum measures using similarities or inner products. The next step was basically we thought that what we can do now is we can actually encode these embeddings in a more compact way by using every second dimension of a real vector to set the imaginary part of a complex number. So now we can take 2 dimensions of a vector and map them into one amplitude variable in the quantum state. And this way we now need only half of the qubits, not half of the qubits, half of the dimensions from the vector to encode, which results in just saving 1 qubit. But the interesting thing is we save 1 qubit. So instead of, what did we have here for GPT vectors, we needed 12 qubits. Now we need just 11 qubits, but the dimensionality of the circuit depth shrinks by 50% because it's linearly dependent on the length of the input vector. So that's significant actually, because this way we reduce errors and so on, and the complexity of the quantum computation with such vectors in general. And so the evaluation was basically, we measure the preservation of the semantic information using similarity scores. So the distance between cat to dog compared to cat to car, and we measure it in the classical world and in the quantum world and compare whether we maintain the scores. One thing to mention here, I didn't mention it yet, is that of course you need in the quantum encoding, you need the vectors to be power of 2 compatible, and this means that we had to pad the classical embedding vectors as well as normalize them. And we expected that as soon as you have to do such a thing, you will probably introduce loss in the encoding, and the similarity scores will differ. We use the Simlex lexicon, which is nouns and their embeddings from the different models, GPT and Voyage and so on. And we built word pairs, measured the cosine similarity or the dot product, depending on the nature of the vectors, and then generated the quantum circuits and measured using the swap test the inner product of the vector representations in the quantum circuit. And we used only nouns for various reasons. I can explain that if you're interested. And got basically for all word pairs computed the classical distance over the embeddings, the quantum distance over the embeddings, and applied then correlation coefficients, and the correlation coefficients were all significant. The correlation coefficient of 1 means that the 2 representations are, or number sequences are the same, or the distributions are the same, and the correlation coefficient of 0 means that there's no similarity whatsoever. And so we got like very good results. We can do that. What that means is basically we can literally take classically trained embeddings and compute with them in the quantum environment without having to face significant loss. Now, when we do that with the complex encoding with complex valued vectors, we get even better results actually on Voyage and GPT vectors. And the coefficient, of course, drops on real hardware. So we expect that this is, of course, due to all kinds of errors internally with the qubits. The effects are basically a lot of these drops and errors in the similarity. Why don't we get 100% similarity? Has to do with the power of 2 padding of classical vectors and normalization requirements and so on. And you know, with swap tests, basically what we have to do is shoot thousands of times the same circuit through a quantum computer and estimate the probability distribution to estimate the similarity score. What we've figured is basically the conversion of real to complex vectors is optimal. It reduces the circuit size or circuit depth, and this means that it's improving the speed and the potential for errors and so on. But still, what we are facing is that all these vectors are not power of 2 length. They are not compatible. We have to pad them and so on. And now the question is, can we avoid this conversion effort and change these vectors? Can we train new models that would simplify and improve our compatibility between classical and hybrid and quantum computers? This is some of the papers that have to do with this exact discussion. If you search on the IEEE site, you will find these 4 papers, and the last one, Old Wine in New Bottles, that's coming out in Springer Nature in the next days. It's actually in press right now. This is what we discussed and so on all the way up to the Quantum AI conference in August this year. Now, what we are doing right now is sort of take the next step, and this means basically we have to change the world. We have to actually train embeddings on the classical world in the classical environment that are complex valued embeddings. And those should be not just normalized, but also to the power of 2 length, fitted and complex valued, so that we can straight away transfer them back and forth between classical and quantum and reuse basically models and store them in the classical world and reuse them in the quantum world and so on. There were previous papers. One of the very good papers by colleagues from Quantinum, for example, that came out in 24 is Learning Complex Word Embeddings in Classical and Quantum Spaces, available on Archive by Harvey and Stephen Clark and Brown and so on. And there's an overview that explains all kinds of attempts and advantages if you actually even do AI and natural language processing with neural models in the classical environment using complex valued neural networks. And some of these advantages are that a lot of properties of language, say speech, for example, or audio signal as such, make use of phase and magnitude, while in simple real valued embeddings, we only take care or encode magnitude. With complex embeddings, we also include the phase, for example. Complex vector embeddings representations are rotation and scale invariant and are ideal for processing transformation robustness, for example, which is what we are doing a lot in AI models, running embeddings through massive, large number of transformations, linear and nonlinear, and so on. And they are important in computer vision and various models of physical world models, which is becoming more popular right now, even in AI, relevant for oscillating data and so on. They improve optimization dynamics in neural network architectures. It's much easier and smoother to calculate the loss and the gradient flow and stuff like that. I won't go into the details here, just sort of an overview why this might make sense to switch to complex valued embeddings. And so what we did is we coded a new system, a new kind of bird. We call it CBIRD, complex bidirectional integration of representation dynamics, which is using the BIRD software, the code that was used by Google and the initial Google team, transformed into PyTorch compatible code. And now what we did is we made it complex all the way through. And the BERT model, just to give you an impression what the neural network architecture looks like, has 12 transformer layers that the embeddings are sent through. And in the base model, which corresponds then to 110 million parameters, and the large model uses 24 transformer layers. These transformer layers include basically an attention layer processing of contextual information over multiple tokens in an input sentence or sequence, as well as linear transformation in a feed-forward neural network, and then processing normalization and nonlinearity activation functions applied to that. So the tokens are piped through from the input till the output through 24 transformer layers, for example. In CBERT, what we implemented is that all vectors and matrix operations are complex now, complex valued. 2 types of activation functions are needed. We implemented one that is phase preserving. That's a very common function. We just implemented it. It's well studied and discussed in numerous publications. And one that is phase discarding, because we want to show and study how much the phase contributes actually downstream in neural network applications that use these kind of embeddings. And the architecture that we built with CBERT allows us to actually include symbolic processing of information, which is unique, which is not what you usually get in large language model implementations or even in versions and variants of BERT. I can say a little bit more about that later if somebody's interested. BERT itself uses as the nonlinearity or activation function Gaussian error linear unit, which is a smoothed function, but it's non-monotonic. While we implemented in CBERT CReLU, which is basically just a ReLU that is applied to the real and the imaginary part independently, and then modReLU, which is activation function that actually preserves the magnitude, its rotation invariant. We have the code available, and we will share that publicly, as well as the trained models and so on. When we build the embeddings, the size of the embeddings, we make sure that they are power of 2 length compatible of complex value dense vectors, so that we can compute with them in the classical and quantum world. So no padding is required and manipulation of dimensionality of the vectors, and they are kept normalized from the outset. We want to train 2 models. We didn't do that yet. We just prepared everything, the code base and the data sets, with and without phase preservation, just to study what the role of phase might be in downstream tasks in AI and NLP. And the core semantic features, the idea here is, while the self-supervision of these AI models, be it GPT or BERT, is to make predictions about a missing word, either the continuation, the next word given a certain context in large language models, or a masked word in BERT. What we add to that is we can make predictions about semantic features or semantic properties. For example, instead of training a model to predict the masked word, we want to train the model to predict whether the masked word is animate or non-animate, whether it's human or non-human, and so on, such semantic properties, and then test whether these properties improve the reasoning capabilities of such models. That's just sort of the next phase for January and February next year. The CBERT code is fully PyTorch based. We used the first version of Jin-Seong Kim's BERT transferred to PyTorch, and then built the complex activation functions and converted the code to be fully complex valued. PyTorch supports that independently, and then the next phase is basically just train the vectors and then apply this model to some downstream tasks like text classification, sentiment analysis, and so on, the typical applications. That's all from me. Here are some more citations of some of the papers that we use that are relevant for this kind of research. And thank you all for listening and staying online. And I would like to hear from you about suggestions and comments.
So thanks very much, Damir, for this brilliant and also nice works everywhere. So that's really nice. I can kick off the discussion myself for is there any difference between the accuracy for models of tokens which leverages words or bits of words than the one that's byte pair encoding? And for what is the ratio of the differences of accuracy?
You know, I'm honestly, personally, I'm shocked that byte pair encoding works as it works over so many languages. My personal perspective would be that I would prefer to deal with real, true language units, words, morphemes, components of words, and how language is composed or language elements are composed. And this means that in our approach, we don't want to address what GPT, for example, OpenAI or Gemini with Google's models and so on is after. They want to handle all languages at the same time in one model. Our goal is primarily to create a system so that we can train a model on one particular language, maybe on two. And we can train it on English, we can train it on Arabic and various other languages, and then see how well we can handle different downstream tasks with these models. The world has changed in the sense that while training such a model like BERT took weeks and months and so on, and a lot of hardware capacity and so on, nowadays with newer technology, newer chips and so on, basically if you have one of the smaller machines of NVIDIA, the pods, training a BERT model is a job of 45 minutes. If you get one of these small boxes, I was just actually in the computer shop yesterday, tempted to buy this thing. It's this NVIDIA Spark device. It's basically a job of a day to train a model of that kind. So, you know, we can do that and we can play around now, and we don't have to go this cloud-based large language model direction and focus maybe on particular languages and real applications and solve that better. This is sort of my perspective on that. So I stick to the tokenizer of BERT is better from my perspective than the tokenizers of LLMs like GPT and Claude.
Oh, I see. That's really interesting. Yeah, thanks for explaining this. We have a question from Abdurrahman Said. He's also one of our pioneers in Quantum AI Lab. Abdurrahman, please go ahead.
Hello. Actually, it's a great work leveraging the quantum computing to calculate the similarity for the two encoded vectors. I see that you have used swap test for calculating the inner product. I was thinking, why not use it could be an efficient method like compute uncompute method, 50% reduction in qubit counts. Yeah, I was thinking.
Yes, exactly. So this is actually we were looking at that, and this is exactly a good strategy. I would do that as well. We did actually think about the variables that we want to control is the tests that we use and how efficient are they and so on. The choice of the swap test was just random. This was the first that we self-implemented, and we stick to that because, you know, we didn't expect that the similarity scores would be worse off. it's of course, you know, the circuit size. If you have to have 2 embeddings, and this means immediately you have already 24 qubits just to encode the 2 different quantum states, right? And then you need auxiliary qubits and stuff like that. So then, you know, you're increasing the error rate potentially in the circuits and in the measures on the hardware, at least. In the simulators, I didn't think that it makes a big difference actually. But tell me more if you think that. I mean, if you have some suggestions and ideas, just send me over. Shoot me an email, and I would really like to hear how to improve that.
Okay, maybe I will send you, and maybe we can work on it together if you want.
Yeah.
Yeah.
So, anyone else? Does anyone have any question? So I can also, I have a question, a second question related to the seabird, because it was also a very impressive model with the way that the seabird is trained, especially leveraging the pairwise, the bit pair encoding. Would it be beneficial for derivations of algorithms and better at coding, like predicting the parts of function code and also making mathematical derivations better? Or how does it compare to GPT and Gemini-based models?
Yes, I mean, there are a lot of aspects to that people start discussing now, you know, about the models as such are textual, they are text-based. Language is not text-based. We are talking with changing the vibration and air pressure, right, in real time. And we also work with multimodal information and so on, right? And so the idea here that some people like LeCun and so on are pushing is that our models shouldn't be language models. They should be rather world models, where we add into the signal flow to train these models expectations about events and things in the real world, and images, data. If we can encode smells, if we can encode tactile information, all that would be significant to improve sort of the properties and the representations of such. You know, if you're sort of encoding in a language model, even just, you know, with the tokenizer that would take words as such, white space separated, say, you know, then you're dealing with ambiguity. The string could mean a lot of different things, right? Contextuality is added by positional information into these models when you compute with transformers. But this is a very limited type of contextuality that does not include the variety of information that have to do with concepts that you want to learn. Also in these models, what we're after, you know, all the large language models and all the approaches actually to process language handle all elements of language in the same way. So every word, every string is just one embedding, one vector, right? But language works in a different way actually. So if I tell you a sentence, I have a piece of chocolate on my table, right? There's a piece of chocolate, and we can have a vector representation for this piece of chocolate that sort of is similar to any other kind of candy maybe. But if I say I ate the chocolate, I ate the piece of chocolate, I know that there was a representation of the chocolate, but it's no longer there. So the function of the verb ate is, it's something like a gate in a quantum sense that converts the representation of chocolate into something new. I knew it was chocolate, but it's now some other representation, right? And this is sort of why we think that I mentioned that we focused on just looking at nouns in the first place. But we think that we have to use the quantum environment actually as a very new kind of philosophical ground to model these kind of processes of how semantics and meaning of things is represented is in n-dimensional space. And so the tokenization issue and what is an embedding and what does it represent is a big thing. And we don't think that we should stick to just sequences of characters in the sense of language text. but add more to it.
Yeah, that's really indeed will be very interesting to explore and to know about. So, so thanks again for all of these valuable answers and all of these nice explanations, and also the great presentation as well. And we are gonna back again to the round table and shortly. So now we are moving to the second speaker.
Thank you.
Yeah, thanks, Damir. Okay. So we have Shweta was us. Jairaj.
Yep.
I'm sharing my screen now to present here. Okay. So Shweta Jairaj is gonna talk about, she is also a quantum computing researcher and a computer scientist, and she will discuss quantum sensing resources and application. Feel free to know more about her work from her, also, and visit her LinkedIn profile to know more about her work as well. Okay, so now we please, Shweta, the floor is yours.
Hello?
Yeah, you are muted. Yeah, now you are.
Oh, okay. Um, sorry. 1 second. Can everyone see? Can everyone see the screen? Or?
Yes.
Okay. Okay. First of all, thank you for inviting me to give this talk at iQafé. I'm really honored to be here. My name is Shui. So I'm just going to give a quick overview of quantum sensors and quantum sensing, because it's kind of a new field. And it's not a new field, but I'm going to be talking about how we used it this year. So a little bit about me. I started the quantum computing group at the New York Institute of Technology in 2020. So we explored tons of applications, from chemistry simulations to financial modeling and AI improvements. And a lot of the students in our group went on to went on to bigger companies where they continued with those kinds of applications. And then we also tested nearly every major quantum computing company to figure out how their toolkits worked, and it's still ongoing. And each year I try to present my research at IEEE or some computer conference. Okay, so first, this is the outline. I'll talk about the background first. So I'm going to go through the background of quantum sensors, how AI and quantum work together, and why AI needed to come first before we could really get into the field of quantum sensing, where the sensors fit in, the existing metrics and benchmarking tools that we can use, and our current research and results, classroom involvement, and upcoming research. Okay, so this is a little bit about the background of quantum mechanics and computers. So we think it's computers to quantum computers, but in reality, it was much more that quantum mechanics led to computers. And we know this through the invention of the transistor, which was a realization of the electric field effect in the 1930s. And so there was fundamental quantum mechanics that was really involved in understanding how these kinds of devices like transistors worked before that there were vacuum tubes, and we need laws of fundamental quantum mechanics to be able to bring us to the computers we use today, which from the computers we use today, now we have software and AI and everything like that. So it was always really the quantum mechanics that was there, and we still need to use our computers to improve the existing quantum mechanics even more. So while physicists and mathematicians developed the theory even back then, computer scientists and technicians and engineers actually engineered the applications. So this is an example of Muhammad Attallah. He was, well, I mean, he pioneered the MOSFET, which is how, if we didn't have that, we wouldn't even have computers. But he was a mechanical engineer, and so he went on from doing that to later doing like cryptography schemes for even security work. And this was also a very big discovery in 1953. General Electric, people figured out how to make the alloy junction transistor through germanium crystal. And so that was really another fundamental step in getting us to the computers we even have today. So upon the invention of the of a transistor, computing completely went. It was allowed to be in full production by that time. So this is also happening in quantum labs even today in my university and universities that I visit around America. I see that it used to be these kind of larger floating tables or these kind of physics setups to figure out quantum operations, but now they're getting a lot more efficient because we're standardizing the processes, and we're also figuring out better materials on how to lead to better, just better materials on and tuning frequencies and more standardization on the processes. There are more quantum labs that begin to talk to each other and better standardize their processes for depending on the application. So this is yeah. So the background is that the transit really helped, and in a similar way, quantum sensors or quantum sensing is going to be similar in that way. So how AI and quantum work together. So there were certain key points that needed to be done through the history that allows us to get to where we are right now. So things like RGB and LED lights. So we are able to even program those kinds of things, which is a fundamentally quantum mechanical process. We understand that the color of the light is directly correlating to the energy of the photons, which is, and that is the amount of energy required to cross the band gap of the semiconductor. So that was only discovered in 1962. And so it was easier to rely on the kind of binary simple physics that was discovered, but it's very possible that we might find that with quantum sensing, we might find that this isn't as efficient anymore with upcoming quantum sensing devices. So digital electronics and AI research was given more importance in the 1970s through the 1980s because commercial computers became practical. But computers are still limited, and like places like Intel and IBM, these are long-standing computing companies that know the limitations of computers. So we understand that we need better quantum devices and better algorithms to inform better computers. So these kinds of incremental improvements really helped, and we're still on the way there to improve computing. So AI is very to even improve existing quantum sensors. They speed up the development time. So like for instance, gravitometers, which are used in gravitometers, are a type of quantum sensor that space agencies use. So they're in post-processing. AI is used to speed that up. And things like optical readers. Without the development of OCR, for instance, which many computing companies use, or we use that on our phones, OCR, when we scan an image. We use AI for that's AI, but sensing can even improve things like that. So where do sensors fit in? So sensors are in use today. Quantum sensing has been in use today. It's already here. We don't have to wait for practical quantum computers to become a thing. One way I like to think about it is that a bad quantum computer can be a good candidate for a quantum sensor, depending on the application. That's kind of a general, it's a very general statement, but the amazing thing about all the research that goes on in quantum computing today is that it's a good candidate for allowing for further research in quantum sensing, which has so many applications. And things like improved accuracy in LiDAR, which is used for 3D modeling of buildings, for instance. Quantum LiDAR really helps with that. There's a lot of I have a lot of papers on UAV image detection. So using unmanned aerial vehicles for improving image resolution through quantum machine learning, as the previous speaker was touching upon, you can improve resolution through QML techniques. And also quantum sensing is useful for telescopes. So deeper tools and advancements are currently being made to understand stars and the universe around us. And it even goes further than that. LiDAR sensors are used for underwater environment scanning. So this was also pretty recent research on using this for an application for improved performance on underwater scanning. So quantum sensors are in use, and they currently fit in very nicely to our existing computing ecosystem. And this was due to the research advancements in the semiconductor industry, which further led to sensor advancements, which further led to quantum computing and the advancements in medicine and climate and many other fields. So sensors, quantum sensing is, it's a very broad and big application, and it's not one application that it gets a lot of popular news is navigation, but it's not just navigation. That's one that many there's big industry interest in, but there's many more applications that can be explored with quantum sensing based off of the research that's been already in existence. Going along with current quantum computing tools that work along with quantum sensing, so we can use the existing community tools for QKD to better inform our quantum sensing developments too. So there's QKD NetSim because quantum networks also quantum networks and quantum internet development is also in the umbrella of entangling photons with light and making measurements with that. So there's still plenty of opportunity for those kinds of tools to work with quantum sensors as well. The tutorial on the sequence program. So that's a sequence is a type of it's a quantum network manager, but a similar kind of thing can be used for making benchmarks on quantum sensing tools. Another another benchmark site is especially for research is NIST has a NIST on a chip, and they give a lot of, especially on this website, they give a way for labs to be able to productionize whatever research they have and implement it. So in 2024, this is the fastest optical clock, which came out due to the Joint Institute Quantum in Colorado. So yeah, so they were able to detect effects of gravity with that they never before have been able to detect. And then so simulations are effective in being able to understand what quantum sensing can do if a classroom doesn't have an actual or a quantum sensor or the materials needed to deploy an experiment. One thing that can be used is VQOL. That's been used by the University of Texas to simulate things like random walks through a visual interface. So this could be something like an actual it could be like something similar to an actual quantum setup, but just through the computer. And that's a good way for students to immediately figure out how quantum effects work and how the quantum sensing and quantum mechanics that they'll need to have. So yeah, so this will go through in VQOL, it will go through what each of these sections mean. So what it means to go through different beam splitters and having these different kinds of objects in place. And it'll go through what each part means. And there's a lot of different examples from the Deutsch-Jose algorithm to quantum random walks on that for a educational optical simulation setup. Yeah, so this is basically from VQOL. They can be able to read out more of their, if they don't have a quantum sensor available, then they can read out results from that. Okay, so current research. So I was at the NYU Abu Dhabi hackathon, and our team was able to develop a program to connect quantum sensing methods for the purpose of solar energy and desertification. So it's already been well known that deserts are ideal for solar installations. It can also, if a map of if a heat map of desertification areas were found, or then it could also be useful for agriculture. But it's good for energy resources, and remote sensing is a really good candidate for this kind of problem. This is only one of the many different kinds of problems that quantum sensing can help solve. And this has been already known that remote sensing can help these kinds of problems. Practical usage still needs to be developed by deploying it. So we were able to make a dashboard and a program, and the paper will also be out soon. So classroom management, or involvement. So bringing the research that maybe someone like me would easily be able to get the most recent research because I get it straight to my inbox because I've been doing it for a while. But the best thing that to do is to do like these workshops, or like that was done at iQafé, was do the quantum hackathon, which is amazing because that's the best way to get hands-on. So classroom involvement is really important for students to be able to quickly understand what quantum sensing is without getting too overwhelmed by any of the jargon, because that's a big reason why many people might not want to do quantum, because they might get intimidated by these kinds of the physics language or the computer science language. And I come from computer science, so I get very, people get intimidated from physics, not knowing the computer science language, and then computer science people don't understand the physics language, so it's a good way for everyone to work together. So there's, oh, I think there's a, I think it was here. This is one way that, or I can share this. So this is one way that, this is generally one way that students can work together to directly get involved in quantum sensors and understanding quantum sensing. So they usually try to choose some kind of application and research an experimentation method, and they determine what the outcomes in future are. So this is just the scientific method, and they can try to do this in 5 days. And I give them existing quantum sensors that already are out. So this is the NV Center Diamond that was put onto a circuit board chip. This is the QV, which was done as a Capture the Flag game at DEF CON last year. So they put a quantum sensor in that, and that was like a fun way for, that's one type of quantum sensor. Or another type of quantum sensing device is this medical device that is available, but that's another type of quantum sensing device, because you can teach students that, you know, it uses nuclear magnetic or magnetic resonance imaging. So just concepts like that. And then another thing is asking the team what they care about solving in their area. So that gets students wanting to use quantum sensing to solve something rather than just making it just about research. Student responses and making sure that that they're not frustrated about things like quantum sensing. Sometimes even adding the word quantum in front of it for no reason it can be intimidating. So it's better to find common ground on practical applications that can be solved and see how most likely quantum sensing will optimize that. And then usually once they get hands-on and experimenting with something like either VQL, or maybe there's another simulation software, or there's a new research paper that they want to improve the code base on, like QML for improving image detection for UAV or something like that, then they can improve that and then write a research paper or publish it or put out a GitHub and then continue on that experiment. That can be someone's introduction to quantum sensing and actual real work that they try to put together in a team. So this can be done in a hackathon context, so this can be just done in a hackathon context. And and finally, it's also important for it to have some kind of small show and tell as well, to see like, oh, this is something that actually is in practice. Like for instance, like the quantum sensor and the FPGA, they can actually see that, oh, it's, even if it doesn't run quickly, they can actually try to see if it, if it works, and they can see the results from that, rather than, the results that are theoretical that they're not able to necessarily see. Or even using, like, if someone is more oriented in understanding diagrams, making different versions of the same diagram to better understand what a diagram is saying is also really important, and really pulls in like the whole project together, because quantum sensing is a very hands-on thing, and so that's also another way to get classroom involvement. So there's various kinds of, so this is still something that's, there's still many areas in this that still needs to get improved and developed on, especially when it comes to quantum sensing. So it's really important for everyone to kind of be on the same page when it comes to teaching quantum sensing, at least. So yep, and then so yeah, so based on what we've already done, so some things that need to be considered is how many sensors are needed for a given task. So say if it's something like quantum sensing for solar energy or solar battery reasons, then how many of these sensors are needed, and that requires like actual deployment, either in academic experiments or industry. And another thing that's currently being looked at actually a lot right now is the computational complexity of these sensors. So would it be more, it's more of a quantum information processing type of quantum information science field, but what is the computational complexity of using this quantum sensing device rather than using a different, like just running a computational model of that. So figuring out the information theory on that is also another benchmark. And improvement of software toolkits. So most of the software toolkits are currently developed by the open source community, and so that they need to, there needs to be further software development for specifically quantum sensing, because many people have been already working on QKD or quantum computing for chemistry applications or quantum networks, but there hasn't been like very explicit software toolkits for quantum sensing, really, because there hasn't been any kind of software toolkits for quantum sensing, and also better communication on the practical application of existing quantum sensors. So like I said, quantum sensors are already existing and they have a lot of practical use. It doesn't need to be so difficult to understand either. They can, I think it just needs to be better communicated so that more people are willing to work together on it. And then also deeper research on open science materials discovery. So shared, so different kinds of materials might be better quantum sensors. And so materials discovery is a very big part of the interconnection of all the different universities here in New York. So I might go to the CUNY City College and go see what their physics department is working on, or they might come to NYIT and they might see like what we're doing here, or what software we're building here, or maybe Columbia or NYU. So this whole like it's a very good thing when there's good collaboration between all the universities here like that. So I hope that can also be there for the global quantum community at large. Thanks. And this is also the quantum Discord server that I have, so if it's useful for anyone. And then also I have a podcast that my friend Ethan was actually doing for 4 years. And so there's a lot of information on podcasts from very well-known and established companies. And also I started doing that podcast too. So if you want to hear more, I'm doing that as well. So if you have any questions.
Thank you very much, Shoei, for this nice presentation and the nice work indeed. And thanks for touching upon the need for software for quantum sensing in Molkit, our startup, which Alan and I co-founded recently. A year ago, we already tried to develop software kits for quantum sensors, especially for the gas-based sensors. And we have developed a use case for ultra-cold carbon monoxide gas as a conceptual use case to detect the change in the laser and also in the interferometers. So when you have a light and it changes the phase, then you can detect that. And then, yeah, we have our own homegrown software and sensing. So yeah, it will be also great to collaborate if you have a project in mind.
Mm-hmm. Oh, that's great. Yeah, thank you.
So I can kick off the discussion of questions. So the first one, you said that all quantum computers, the bad types of them, which are not good, can be used for quantum sensors. Are all types of quantum architectures suitable candidates to be a quantum sensors, or specific types of them?
Oh, no, not all types, because they're very ingrained in that type of architecture for specifically some type of quantum computing purpose. But like certain kinds of quantum computers can be very good quantum sensors, especially if they are doing some kind of entanglement and it's noisy, and they can be a good candidate then for quantum sensing, as long as it's put into that kind of framework of quantum sensing. That's just what we need to get more people to think about in changing the framework a little bit for just that application. But they can work alongside each other, quantum computing, because quantum sensing works along with quantum computing. There's sensing going on in a quantum computer anyway. So.
Okay, that's really great. Yeah, thanks for the answer. Is there anyone have a question? Yeah, please, Damir, please go ahead.
Yeah, I'm just wondering, I mean, when you think about these big efforts with quantum computing, everybody's just talking about cloud services and high performance computers, IBM and so on, but actually for sensing, you probably might be interested in something like embedded quantum computing, rather, small devices that actually process qubits directly, right? Photons, for example, and so on, rather than converting them to classical and so on. So I'm wondering, is there something going on? Are you aware of developments in this domain?
Yeah. So the embedded quantum devices are useful for things like Intel or micro like AMD. They've been doing they've been working on embedded quantum devices for like maybe since the 90s, but they've been trying to contain, and AT&T and Bell Labs, they've always tried to understand how these quantum effects work together, and they've tried to reduce the size and reduce the size and reduce the size. And I think that might be the whole point of these massive data servers working with NVIDIA, and relieving some of the load off of that, because they just can't handle that. We just don't have the quantum sensing capabilities fully built yet in order to get where it needs to be, because I think computers already are suffering from that bottleneck.
Yeah, thanks for the answer. I will also I can ask a question, because we are trying now to develop a code which can work on an analog chip, so it's associated with the sensor. That's also related to the question of Damir. It doesn't need to go to be processed at a remote server or remote location. It's processed on the chip. So what do you think about the current works in this, and how this can help the market of quantum sensing?
Oh yeah, I think it's great. I actually meant to touch on that earlier in the history, that there was a switch that happened with digital electronics that I think newer analog devices that have more quantum enabled effects in them could really massively improve applications. I think a lot of the analog quantum sensing ways to do things is really a good way. Yeah.
Yeah, thanks, Shui, for the answer. That's really great. Does anyone have any question? So if not, I would like to thank Shoei again for the nice and impressive presentation. Thanks, Shoei, for being with us. I would like to ask you one last question, very small. If you are gonna organize a future hackathon and would like to add the quantum sensing part to it, what kind of activity the students need to be prepared before they go for the hackathon, for the participants?
Oh, that's a good question. Yeah, if there's a quantum sensing part of it, they could learn about what happens when two different things like the double slit, basic things like the double slit experiment, and what happens when you shine a blue light to another blue light, like just seeing effects like that. And then also some math would be good, definitely, to understand what those actually mean. And that can be understood by, like, for example, using vql.org or Quantum Flytrap is another great simulator that they could actually really prepare to see like quantum mechanical effects. But I think in terms of backgrounds, if they have the same quantum computing knowledge, it would be more intuitive if they already understand quantum computing to also understand quantum sensing.
Okay, so thanks for the answer. We have one last question from Ziad. Do quantum sensing have applications in learning algorithms domain?
Yes, yeah, definitely. So quantum sensing can be used for, like, there was a slide I was showing on optical readers. So, or OCR is a very common, machine learning. It's machine learning. So the question was, does quantum sensing was the question, does quantum sensing work alongside with reinforcement?
Yeah, maybe Ziad, can you explain your question? Give it more context. So maybe he's asking about if it can help the algorithms, as far as I understood it, if it can help develop in the development of algorithms, like by giving data that can enhance the quality of algorithms.
Yeah. So so quantum sensing can be used to improve AI, and then and like on a very low level computing scale, but then AI can be used in post to improve maybe improve like some aspects of a sensor. Like for instance, like maybe MRI machines, they perform the task, but then in post there's a lot of software development that also and learning algorithms that will make the performance better. There was a archive article that I gave about how they used quantum machine learning methods like neural networks to improve upon an existing like a UAV application.
So I think that's maybe the point of the question. So I would like to thank you, Shoei, again for the nice work and for being with us. Thanks again. And now we are going to move to our next speaker.
Thank you.
Yeah, thanks. So our next speaker is Mr. Alain Chancet. So Alain is the president of Molkit SAS in Paris, in France, which the startup that I was talking about earlier. And he will discuss the power consumption analysis for the SQD simulation of the molecule CH2 singlet molecule. Also, feel free to visit Alain's LinkedIn page to know more about the recent work and the bio, and our website, molkit.io. Okay, so Alain, the floor is yours.
Well, thank you, Tara, for inviting me again. So I will just try and share the right thing. Okay, I think that's the one. Okay, so hopefully you can see it in big size. Hopefully.
Yes.
Yes. So today it's a new perspective on a topic I've addressed a number of times, including in this series, Quantum AI, and also more recently Quantum Fest, IBM Qiskit Quantum Qiskit Fest festivals for Nairobi and Argentina. So it's my pleasure to be here again. It's not a lecture. It doesn't require any prerequisite in terms of chemistry. Don't worry, and there is a glossary at the end. So and there is an extensive bibliography, and we will share the deck of slides with you. So let me see if I can move this one. No, it doesn't work. It's usual. Okay, partager, modifier. Okay, so it doesn't seem to. Okay, let me try.
Can you click on the arrows, the left and right arrows?
Yes, I can click on them, but it doesn't move.
Doesn't move always.
So let me try something else then. Just bear with me. It's the usual effects.
Yeah,
Okay,
definitely.
so let's try again. I've got another hopefully way of presenting this. I will present the whole screen, so there might be some weird effects. Can you see my screen?
Yes.
Yes. And this time I can move around. Great. So, yeah, I mean, in a nutshell, first of all, I'm not an academic, but I'm proud to be an advisory board member at North America Technical Institute, NATI, and I guess someone from NATI is attending this event. So this is the only credential I have in academics. Recently, and I'm grateful for Nancy, who is among the participants, to be in a team which won a challenge, the Market Split Challenge, during the IBM Quantum Developer Conference of this year. It was in Atlanta. So I'm really grateful that I was part of this team. It's really an honor. Thank you, Nancy. I'm a co-author of a book which came out in 2022, Quantum Chemistry and Computing for the Curious, and the lead author is Dr. Kipel Sharkey. She's taught me quantum chemistry, and I focused on the understanding, of course, the topic, but also illustrating with Python and Qiskit codes. There is an executable version of the book. There is a repo on GitHub by Pact Publishing, and I've got another one which I try and maintain as best as I can to make it work with the latest and greatest version of Qiskit. So if you're interested in variational quantum eigen solver, quantum phase estimation, and also an introduction of quantum chemistry and quantum computing, then I really recommend that you purchase the book. Okay, I've also proudly have been published in a peer-reviewed journal pertaining to the quantum permutation pad with Qiskit runtime, and I think I made a couple of presentations not so long ago. I've been pertaining to quantum permutation pad, a speaker at the IEEE 14th International Conference on Communications, Circuits and Systems in Wuhan, China. Actually, I held this my presentation remotely. I've also been a panelist at the QADC Quantum and AI Use Cases panel. I was earlier this year a speaker in this Quantum AI monthly series. Okay, so let's move on. So yes, so this is the so the market split problem is a resource allocation task that becomes computationally intractable even for relatively small instances. And it's one of the 10 problem classes that make up the quantum optimization working group's intractable decathlon. So you've got the list of members of the winning team, and there are links to the post by IBM, and also if you want to get your hands dirty trying to figure out what it's all about, then there is a link also to the actual Jupyter Notebook. Thank you. Okay, so everything I'm going to talk about is public, and it's basically my GitHub repo, SQD, underscore Alain, that's my first name, and it is maintained very regularly. You see the date yesterday, I took that. So feel free, and there is a link, feel free to visit my repo, and it's well documented, and of course your feedback matters. So far I've got only 6 stars. Okay, so the agenda for today, first of all, I will present the scope and the vision by IBM Quantum and their partner Pascal, what they call quantum-centric supercomputing. In this context, I will introduce what sample-based quantum diagonalization, SQD, is about, and illustrate the why it matters with 2 use cases, and then we'll focus on the SQD, which is applied to open shell systems, and this is where we will end up doing my demo of the energetics analysis. So it's a new topic, the new perspective of a topic I've already addressed a number of times. So, okay, so quantum-centric supercomputing is considered to be the future of high-performance computing, HPC. But the great interest is that it hopefully enables us to achieve near term, that is to say as early as 2026, quantum advantage in chemistry, material science, and other scientific applications. And if you wonder what a quantum-centric supercomputer is made of, well, no surprise, it's made up of quantum processing units, QPUs, graphical processing units, GPUs, the kind of chips you see in high-performance computers, not just laptops, and CPUs. Okay, and I put the links for the corresponding definitions. Now, sample-based diagonalization. I've chosen the. So I hope everyone can see my screen here. This is a functional definition. You don't need to have even a master's of science in chemistry to understand this definition. It's initially it's a chemistry simulation technique. Now later on it has been applied to other fields depending on some features of the Hamiltonian. And in a nutshell, it uses the quantum computer to extract a noisy distribution. Why noisy? Because current generation of quantum computer, they suffer. They are not perfect yet. They are not error corrected, so they are so-called noisy. Distribution means a probability distribution. So the outcome of a quantum circuit, even if we run it a large number of times, 1,000 times or maybe more, the probability distribution is not what we would expect if the theory was applied perfectly. So it's a noisy distribution of what? Of possible electronic configurations of a molecule, and this distribution is in the form of bit strings. And so on the left-hand side, you see a diagram which summarizes. So the first step is basically a classical. FFSIM is a package. For more details, please refer to my glossary at the end. So the first step is to create a so-called LUCG quantum circuit, which doesn't come out of a quantum fluctuation or thin air. It's actually it leverages some well-known classical methods in quantum chemistry. By the way, quantum chemistry has existed for decades, long before quantum computing became a buzzword. So quantum chemistry basically means chemistry from first principles. And so the first 2 steps is basically classical. And then we have a run on the quantum computer. But the interesting part, at least this is where SQD is known for, it's an iterative correction, which is entirely on a classical computer. So it differs from variational quantum algorithms like VQE or QAOA, which have been and are still popular to a certain extent, which have been around for several years now. But IBM and other key thought leaders hold the view that in order to make progress, we need to move on, and SQD is a promising new algorithm. Okay, so this is the interest. So the idea is that this, and I will move on to the next slide. Okay, sorry. So it's a very elegant, self-consistent configuration recovery loop, and it can be parallelized. So in a nutshell, instead of having to deal with an intractable quantum diagonalization, which means diagonalizing a huge matrix, because basically in quantum chemistry, like in quantum physics, we have got to solve the so-called Schrödinger equation, and it boils down to solving a large matrix, and it turns out to be beyond what can be done even on the most powerful high-performance computer. So the interest of this approach is that instead of having to trying to solve an impossible too big matrix, it is broken down into a smaller matrices, and so yeah, it makes it possible to solve the problem. So I won't go into details. It's I think what matters to understand is that the big difference with the variational quantum eigensolver and the variational algorithm is that the iteration, it's only on the classical side. Okay. Now, why does it matter? Why are folks so excited about the what SQD can do for us? Well, there is this use case, a fruitful collaboration between IBM, Cleveland Clinic, and RIKEN in Japan. They have the most powerful HPC in the world, Fugaku, together, and that means a synergetic collaboration of a multidisciplinary team. It's not just the tools and technology. They managed to simulate the ground state dissociation of the nitrogen molecule N2, and also clusters 2Fe, 2S, and 4Fe, 4S. And I did that with SQD in the context of quantum-centric supercomputing. So what that means, you use the Heron supercomputing quantum processor. So there are several generations of Heron 1, 2, 3, and the latest one is Heron 3, and a supercomputer. And what is interesting is on the left-hand side, you see with today's version quantum eigensolver on today's QPU, that is Heron, IBM, and I refer to Antonio Mezzacapo, a brilliant presentation. Is a video which you can watch on YouTube. It's highly it's enlightening, and it's easy to follow. No prerequisite required. It would take 3 million years. Well, it boils down to it's basically intractable. Okay, so forget about VQE, at least for that kind of simulation. VQE might still be of interest, or variants of VQE for other topics, but unfortunately, that's the way it is for quantum chemistry. That kind of simulation it's intractable. Even with a better algorithm, quantum phase estimation, on fault-tolerant QPU, which we don't have today, it's anticipated it would still take 13 days continuous. Imagine running a continuous an experiment for so long without any incident. If anything happens, well, it's the fragile quantum state is measured, and you've got to start all over again, unless, of course, the algorithm has been designed for that kind of event. But the good news is today, just in just 2 hours, SQD within this quantum-centric supercomputing framework, one of the best, if not the best, Heron superconducting quantum processor and the supercomputer Fugaku, they managed to simulate this, make this simulation just 2 hours. So I think this is reason why we have so much interest, so many papers. Like every 2 weeks there is a new paper about SQD. Okay, so another interesting use case. This time collaboration with Lockheed Martin and IBM. It's about chemistry simulations with SQD. Their study is relevant for interstellar as well as combustion chemistry for rocket plumes, basically. And so basically it's about the dissociation of the ground state. So it turns out that the CH2 molecule known as methylene has got two states, and the two states they interchange with one another depending on the energy level. So this is what is summarized on the left-hand side. You see the singlet. There are two configurations, and the arrows represent the spins of electrons. So you see in the singlet there are two electrons which are opposite spins, one up, one down, on either 3A1 or 1B1 orbital. Whereas on a triplet, the electrons each occupy an orbital, but their spins are both on the same side. Okay. And what is worth noticing is that at the time this experiment was made, the researchers had access to the most powerful IBM quantum device available at the time. There was only 52 qubits. Now, I've been able, the experiments I will share with you in a few minutes, I've been able to use with the IBM, the free plan, 10 minutes free per month. I've been able to access Heron 2 chips, machines known as IBM Phase, and what's the other one? They both have 156 qubits, and remember that at least in theory, when you add one qubit, potentially, the size of the Hilbert space is multiplied by 2, so potentially you have got twice as much power. So imagine going from 52 qubit to 156. It's huge. So it means the speed of a change, the speed of improvement. Imagine that anyone who is entitled to gain access to the free plan can now make experiments that just a year ago were cutting edge. Okay, so I think it's absolutely amazing. So without going into details, just what they have achieved, they have managed to capture accurately what is called the first order phase transition, and I will explain that with the diagram on the left. You see 3 sets of curves with different colors. There's blue, unless you're color blind. There is a kind of blue, red, and yellow. And so the singlet is represented by like a tripod, and a triplet just dots. And what's interesting is that these curves, you see, take the red one, the one which pertains to the triplet with dots, and the one which pertains to the singlet with triplet, they cross one another at a certain distance between the carbon atom and one of the hydrogen atom. So they cross one another. And what's interesting is that the SQD, which is in red, is almost as good as the SEI, which is the best simulation that can be achieved with classical method, but on a very powerful computer. So yeah, so they are happy that they were able to capture accurately exactly when that happens, and it turns out that matters for both interstellar and combustion chemistry. So I think, okay. So now it's time to for me to show off what I've done. So first of all, a few very important assumptions. I don't know, and maybe only a few engineers, folks who are working with IBM have an idea of how much their quantum devices consume in terms of energy. So we make an assumption, and I refer to an article which was published by Capgemini in 2023, and it gives a ballpark figure that, not just IBM quantum computers, but more broadly superconducting quantum computers, even if they are idle or lightly used. There is good reason to believe that the power consumption it's between 15 and 25 kilowatts. Well, that sounds reasonable because a personal laptop, basically it's a few hundred watts. A big personal computer, maybe 800 watts, maybe even 1 kilowatt. Yeah, it doesn't. I mean, bear in mind it's not just the because the pure quantum part, which is the quantum what makes the quantum the qubit alive, it is only microwatts, okay, but it's basically the all the infrastructure around the cryogenics and the control logic, which is classical, and that requires some power. Okay, so that's the first assumption. So, and you will see in my implementation, I actually leave it up to the end user to pick up a number. Okay, right. So the classical simulation. Okay, so in my examples, I illustrate scenarios where it's pure classical, and I've used a trick, that is to say, using random samples which are drawn from a uniform distribution. A uniform distribution is obviously much worse than the kind of probability distribution you would expect as output to a decent quantum circuit. And so it's presumably the worst starting point that you could think of. Now this turns out it works for small molecules and for basis sets. Basis set is basically a collection of mathematical functions that are used to basically stimulate the wave function of electrons. Okay. There is a definition in my glossary. So the thing is, for all the experiments except one, I will share with you, this classical simulation by generating random samples appear to work. However, there is a caveat. It will fail for larger and more practical problems. Okay, so and finally, last but not least, my implementation of SQD integrates a package which is known as Eco2AI, which I discovered just a few weeks ago, which is a Python library which accumulates statistics about power consumption and CO2 emission during running classical code. And it's licensed under Apache version 2.0. So having made those assumption caveats, I can go back to the, so some of you might have already seen this, but there are new participants, so bear with me. The singlet, so-called singlet state CH2 molecule, okay, 631G basis set is one of the basis sets which are popular in quantum chemistry. So again, a basis set is a set of mathematical functions, and I explain more in detail what 631G stand for. Best to have a look at the right-hand side. You see the singlet, the 2 electrons in the carbon atom are paired, and 1 orbital is empty. So you see a diagram on the right-hand side. At the top, 1B1 is empty, and 3A1, there are 2 of them with opposite spins, and it's the converse for the other one. Okay, and so in a singlet state, the 2 electrons are paired with opposite spins, resulting in a total spin of 0. However, and this is the kind of thing that would make LLMs happy or not. It turns out that with PyICF, which is the popular package, Python package used to make classical simulations, they have another definition of spin. With PyICF, spin, they mean the number of unpaired electrons. So it's the reason why in my configuration I will share with you in just a few seconds, the spin is the value of spin is 2, whereas actually from a pure quantum chemistry standpoint it's 0. Okay, so it's one of the things which I think illustrate the challenge of the different well, even within quantum chemistry it's unfortunate that the PyCF package, they don't follow strictly the well-known definition of spin. Anyway, that's the way it is. So there is a Jupyter notebook. I won't go into there, but we will see screenshots. Okay. So what happens is this. So this is the if you want to make experiments, and I wish some of you participants do experiments, there is a so-called Gradio user interface, which I discovered last year when I did my study to get the IBM AI developer professional certificate. It's a very user-friendly user interface, so that all the parameters that you need to run an experiment, you can first load from a file, a JSON file, for example, the experiments I've already run, and then you can make small changes. So, for example, you can change 631G to a better basis set, CC PVDZ, for example, but at the expense of maybe it won't work. So that's why compute exact energy, which is more for the purpose of having an idea at the end whether the quantum simulation was good or not. Sometimes even on my environment where I only have 32 gigabytes memory available for simulation, it blows up. So you can untick this. And sometimes the bottleneck is actually on the classical side. If you choose a basis set which is good, and there are many electrons, then on the classical part it may not be able to take off. Okay. Anyway, the good news is that you can load predefined configurations. In other words, so singlet is where we have a spin of 0. Okay, that's okay. And this is the new feature which I added a few weeks ago. It's the Echo 2 AI tracker, which lets you enter the information, which then makes it possible to get the information, how much energy, how much time and energy was consumed on the classical side. Okay, so there is also a more another way of entering the information, which is maybe less comfortable, but lets you gain access to all the parameters. Okay, so what's interesting, and there is another table like this, is the outcome across 3 experiments. So same basis set. You can see in the table. So there is CH2 singlet. So my experience in that case, no QPU. Just leveraging the ability to get random samples from a uniform distribution. Obviously ends up being the winner in terms of energy spent. Then there is the first simulation I made with just 1,000 shots on IBM phase, and then there is another one with 50,000 shots. Now, what's interesting in terms of chemical accuracy iterations, the number of iterations you need to reach the so-called chemical accuracy, is that actually the best one is the one which may not be a surprise, but it's good to see this actually works, is that the more number of shots, that is the number of times you're on the quantum circuit, the higher it is, the better starting point you get. And it's no surprise that this ends up being the winner. So in other words, with this simple experiment, the classical simulation consumes less, but the one which is most efficient in terms of number of iteration is the one on the IBM quantum device with the largest number of shots. So I think it points to a need to manage an optimization of on one hand performance efficiency, and on the other hand energy consumption. Okay, but we shall see another example this time with the triplet. So it's the same. So you have seen this already. So I can move on. Basically, yeah, we have got 2 unpaired electrons which are parallel spins, leading to a total spin of 1. Yep, but but actually, yes, and a spin of 2, because because there are 2 unpaired electrons. So the definition of PyCF, I need to put spin of 2, whereas from a quantum chemistry standpoint, it's actually a spin of 1. Okay, so this is very similar. Same formula, and so this times it's only 1,000 shots. Okay, but this is a triplet, and this is what it looks like. So it does convert. This is the so-called chemical accuracy, which is 1 millihartry, which is 10 to the minus 3. So it takes about 6 iterations to reach to go beyond the chemical accuracy. Okay, and then there is the average occupancy per spatial orbital, which meets what's expected from the theory. Now, I made another experiment, but this time with the other interface. This time I bump up the number of shots, 50,000. Wow. So let's have a look. Yeah, it's much steeper in terms of curve. So basically the convergence is achieved in just 4 iterations. So again, if I go back 2 slides above, you compare this. Okay, IBM phase 6 iterations, and now, yeah. So that's really good news, because it means that the SQD, yeah, it does work, right? It does work. The more effort you put on the quantum side, that is to say the number of shots, you would expect that it would lead to a better quality output probability distribution, and then that the recovery would get to the chemical accuracy and beyond in less iteration. That is indeed the case. Okay, so and this is the analysis. So again, with no QPU in terms of energy, it's indeed the winner. But in terms of chemical accuracy iteration, the number of iterations required to reach or even get better than the chemical accuracy, the best result is achieved with the scenario where we have the largest number of shots. And recently I made an experiment which is available on my, so maybe if we're, Taha, how much time have I got left?
Yeah, there's a few minutes. Yeah.
Okay, there's a few minutes. So maybe I can take the risk of going to yeah, my I don't know if you can see my.
Yes.
Can you see my?
You can see the GitHub. Yes, yeah. You can
Okay.
see the browser.
So
yes.
so this is well documented. So don't worry. Installation should be easy. How to set up your own, because this is what I think is fun, exciting. Is that almost anyone with. I mean, this is very simple to install. I mean, you can run your experiments. Again, experiments that just a year before, 2024, it was cutting edge and was only top researchers who were lucky enough to have access to the hardware that enabled them to make. But now it's possible. Okay, so there is the information about the energetic analysis, how to make it work, and then we have I present a bit of theory, so you don't need to, and then I present the different experiments for different molecules. So it's explained how to do things. So CH2 singlet, we have seen that, triplet. But what I want to show you is something really recent, which I did just a few hours ago. Yes, just a few hours ago. Is it N2? Oh no. Oh, okay, so it's not in there. So it is there. Sorry. Yep. Okay. So this is the one I made just a few hours ago. CCPVDZ is better basis set than 631G, and I tell you what, I was not able to run the simulation with the random samples on my laptop because it blew up basically. So in the case of N2 with this basis set, the classical, pure classical scenario is out of the game. It can no longer be considered. So you see, I think it's important. And so there is a plot also. So it's struggling a bit more because there is the very large number of electrons the key, to summarize quantum chemistry, the challenge is to get accuracy, because otherwise it's of no value, okay, basically, but at a reasonable cost. And it's really a trade-off, because unfortunately, as well it is, the complexity, so computational complexity goes up exponentially with the number of particles, i.e. the number of electrons. And so for the last decades, people have come up with a clever way of making this manageable. And in particular, my co-founder, Taha, his PhD thesis is about a clever way of making the simulation of collision of I think CO2 and helium manageable, and this takes so much effort. And so it's no surprise that yeah, for N2 it takes more iterations. But I wanted to show you that because it means, yes, that run on the so this is the where is the oh yes, that's the notebook. So I use the Gradio interface. So yep, I think that's it. Anyway, anyway, so I wanted to share that with you. So now I can go back to maybe my presentation. And just to conclude, there is a glossary of terms. Also, for those who are interested, just a quick comparison of a few basis sets to see that there is not one size fits all, but so okay, and a bibliography, and there are some very recent papers. You see, 30th of November of this year. So this is a hot topic. This sample-based quantum diagonalization is very promising, but it's really early, and so there is work on that. Now I'm ready for questions, if any. I will stop sharing now.
Yeah, so thanks very much for the nice and also beautiful work on SQD and the energy. That's very impressive work indeed. I can also start kicking the discussion. So now we see the energy goes higher with the complexity of the computations. Are we? Do you think we are going to need algorithms which can optimize the algorithms to be able to run it on quantum computers for large computations? So when now the size of computation goes higher, then the energy demand will go higher, or do you think we are gonna reach a saturation? Larger computation will still be enabled on quantum hardware.
So thank you for this question, which is really relevant. I think there is something. So far, I mean, the assumption pertaining to the power of a quantum computer superconducting loop, typically IBM quantum devices or Google, they are very humble, very reasonable. We know from the IBM strategy that IBM are really confident that in the next coming years there will be huge improvements in terms of energy consumption for classical computers, but particularly because the bottleneck with classical computing is moving data from memory to the processor and conversely. So, but of course that will benefit the integration of high performance computing and quantum computing. But I would like to point out that another Frenchman, Olivier Ezrati, has made a bunch of talks recently, including one in the United States, and his topic is quantum energy. He's the co-founder of the Quantum Energy Initiative, and he has presented in his talks. He mentions that the range of power for fault-tolerant quantum computers, okay, of all the technologies, okay, the range of consumption, of power consumption, goes from 1 to 1,000. Wow! So it means basically it could be that some of the most performant, some of the fault-tolerant quantum computer that would enable some computations, particularly in quantum chemistry field, would be extremely greedy in terms of energy. And that could be an issue because already we have with large data centers for LLMs we are running out of energy, right? So it's apart from IBM, where I think there are good reasons to believe that they will be successful in taming the increase of energy going from the current generation, ever improving, but still noisy, to fault tolerant. But other technologies, it's widely unknown. And again, I mean, in my repo, SQD Alain, at the bottom there is a bibliography, and I provide links to presentation by Olivier. So I guess that answers your question, or that opens a new question: is can we anticipate how much energy will the fault-tolerant quantum computers need in order to solve practical problems, especially in quantum chemistry? And the answer is the level of uncertainty seems to be even greater than what we currently have. So that's the way it is.
Yeah, definitely. Yeah, thanks, Alain, for the answer. And we are gonna carry with us. We are gonna carry out this question with us to the round table, indeed. So, is there any question? Okay, so we will see. Habiba has already wrote a question in the chat. Can you say it? Can you talk in the mic?
Hold on. Let me see if let me have a look at the chat. So Nancy, Nancy, thank you for leading our team to be a challenge winner. Thank you so much. Okay, if QT only works on very small molecule and fails on larger ones, and what can, okay, so the hope is that SQD would actually work on bigger molecules. That's the whole point. Otherwise, it would be there would be no point carrying on studying this. It turns out that with what I have, for instance, at the moment, I only have access to the free plan of IBM Quantum, which is great, and my humble laptops. So that this is the limitation. I would say that if I could get a hold of a larger workstation with, say, ideally 1 GB of RAM, then wow, yeah, that. So actually, the limit is more. It's similar to what happens with large language models. Actually, it's not so much the power of CPU, GPU. It's more the amount of memory. Okay, and so yeah, I mean, I'm confident that even today, I mean, what I've shared and what you can see for yourself with my SQD Alain repo, small molecules, yes, it's a piece of cake. It's really easy. But of course, we can only demonstrate that with SQD we can reach the same level of accuracy as we can with PyCF and Python. But it is nevertheless a proof of concept. Because again, I mean, the higher number of shots, the better the starting point. So I hope I've answered your question. So yes, hopefully, yes, will be for much larger molecules, but that will require a tight integration, quantum-centric supercomputing, basically tightly integrating what is today two different beasts. Okay, HPC and quantum. The two need to be tightly integrated, and with innovation in terms of hardware. That IBM, among others, they anticipate will happen in the next coming years. I hope I've answered your question, Nancy.
And we have another question from Habiba. Are algorithm level optimizations more effective than hardware level ones for reducing power consumption in SQD simulations of CH2?
So this is a very interesting question, because actually, so I'm more like an experimentalist, okay? So I like to try a different scenario and see what happens. There is something to bear in mind also. I noticed that for CO2, carbon dioxide, is that because of today's limitations in terms of number of gates that can be executed before decoherence start to become important, it turns out that for slightly larger molecules, my perspective is that the noise level, which is a level which basically defeats the good value of the initial probability distribution. So basically, so I think it's an open research topic. It's an open research topic, and it's not just XUD simulation of CH2. It's not just quantum chemistry. It's the whole thing, because when you think about it, unless of course it's to solve the Haber-Bosch, the famous challenge in chemistry is to find a way to produce ammonia with much less energy. Okay, but this, even if it requires a simulation that requires a huge amount of energy, once the outcome is known, and that's it. I mean, it could be a Manhattan-like project. It's okay, but for other purposes where there is a need to run the algorithms again and again, then the energy consumption matter, and I think that ultimately someone will have to pay for that. Okay, so the entities, the companies which will provide access to commercially available quantum-centric supercomputers, somehow they must make a profit, right? So the end user will have to pay. So the price per minute, or if not per second, of these machines will be linked to the energy consumption. That's for sure. So and of course there is a trade-off, because maybe some applications it matters to have the answer within a few minutes or hours, but for others you can afford to wait for several weeks. So if it's okay to wait for several weeks and have a lower energy consumption and a lesser cost, then that's fine. So that's a very interesting topic. It's optimizing performance versus energy, and it depends on the priorities, on the use case, but there could be more or less generic methods to a problem, but classical, I would say. Maybe that could be run on a quantum computer as well, like a QBO, or like an optimization, basically. A new topic for next year, the next developer conference, presumably find a way to optimize and run it on a quantum computer. Okay, so thank you for these questions. Very good.
And thanks, Alain, very much for the clear answers and the discussion about the questions, and also the nice work and impressive work about SQD energy consumption. Now we are moving to the round table. I would like to introduce one extra panelist who is going to join us now. So Ahmed Salim is a senior technical leader and the quantum ambassador at IBM Saudi Arabia. And he also gonna provide an overview about the quantum software ecosystem, and also make reflection and draw some answers from IBM Quantum Summit, which we already have attended together with Alain and Ahmed and myself in Amsterdam in November 2025. So welcome, Ahmed.
Thank you, Taha, for having me today, and welcome to all the panelists and all the audience in this talk. Thank you very much.
Yeah, thanks again. So I would like to start with you and the questions. So first, this last series was very nice, because we had discussions between the LLMs by Damir, and also the state-of-the-art models to absorb the semantics and the expressions in the language and have a better models. So that's one of the hot topics in 2025. And plus that, we have the quantum computing and also the associated price with it, which comes from the energy consumption to do this accurate computations with quantum, and also use the hybrid workflows. And we have the quantum sensing from Shewi, and also Shewi has already demonstrated the need, and also the quantum sensing. So we have a blend of technologies. So far, with this, we know the rules of the game. We have some constraints from quantum, but also we have a lot of nice promises that are gonna be achieved hopefully in the near future regarding quantum technologies. And here comes the first question. So one of the things that has been demonstrated during the summit is the way that we move from the increasing the number of qubits on the chip to the modular design. So like from more qubits on a single chip to interconnected chips. So in your opinion, how this will bring the quantum advantage for practical use cases?
Okay, well, thank you, Taha, for this question. It's a really important one that I can see, and I can tell from IBM perspective and the roadmap that it's published online. IBM is moving from quantum system 1, which has one processor, one quantum processor chip with multiple qubits, regardless the number of qubits, to quantum system 2, which is a modular quantum machine, which has multiple chips working simultaneously as a one system. And this has been achieved by the quantum chip called the Heron. And we have 3 versions till the moment of Heron. And the latest version, which is R3, it has 156 qubits. And these and qubit and the Heron chips, actually, it's a very special generation, because now we were able to build multiple quantum system working simultaneously as a one system. And definitely this is one of the way of one of the steps toward the fault tolerance quantum computers, where we are building like an heterogeneous environment to get the benefits out of the quantum and the classical computers, like what Alan explained in the SQD algorithms. It's this is one of the best and the most obvious examples of having a hybrid quantum systems, where we have quantum processors working hand in hand with the supercomputers, which is what we call it now classical computers. Regardless, it may be a super computer, that it has a very powerful processing units. So yeah, this is the way that IBM is trying to achieve, to scale and have multiple chips, quantum chips working simultaneously as a one system. Other than that, we will be on the same trap, like we have the same capacity limited with the space when it comes into the number of qubits that we have. Yeah.
Yeah, so that's really great to know. So in your opinion now, of course, this will be better than the monolithic chip approach. So what this, for example, will bring the verification of the quantum advantage closer to us? And if yes, in what sense? In which applications?
Okay, yeah, IBM now, it has, if you look into the roadmap, it has 2 different types of roadmap. The production roadmap, which is going commercially to the market, and the research and development roadmap. And in the last Quantum Developer Summit, IBM announced the 2 new chips, Loon, which is one of the milestones in the research and the development, okay? And this chip, it comes with a new way of connecting the qubits on the same chip, what you call the C couplers, okay? And this will enable to do entanglement in a qubit on a distance, so we can do a better processing, much deeper circuits. And on the production level, we have Nightwalk processor, which is, this will pave the way to the fault tolerance, because Loon processor, we consider it as the first step towards building a quantum memory. And from all the new or the today's sessions, like what Demir is proposing, show us, and Alan as well, I think the quantum computing will not survive or will not reach to the fault tolerance unless we have a quantum memory. And this is one of the main components that we can see, and it will be a key player. Because now we don't need to do the heavy load of having or dealing with the classical data and put it in the processing and doing an encoding into the processing unit. We can have, for example, in the quantum sensing, we are using quantum sensing. It captures quantum data, and we need to save it in a quantum memory. We don't need it to transfer it into a classical to be able to move it to for processing. You know what I mean? So we are trying to close this cycle and have it quantum all the way, starting from capturing the data till the processing and getting the outputs.
Yeah, okay. That's really great to hear. And for that, I will draw now the line to Damir to ask about the efficiency of LLMs. Also, having the input from Ala about the experiment of SQD, and I'm gonna back to him in a second step. So first, now the LLMs will demand huge computational power. I mean, there is like the Thrive and also the notion of having modular nuclear reactors to supply the power and so on. So, do you think the training of LLMs on quantum computer would deliver or would be much efficient than the classical computers in the near future, or what's your perspective on this?
Yeah, I want to believe, and I would trust Elaine more on being able to estimate that. You know, the story that we hear from colleagues here, in particular in sort of the quantum hardware industry, is that exponential growth in quantum will require just sublinear growth in energy demand, while linear growth in classical requires exponential energy demand. And on the long run, I believe that the future of AI systems of the type of LLM, something that is cloud-based, offered by OpenAI and other players, this will actually drop in demand and importance. What we see is already democratization of hardware and the possibility for small groups with low investment to actually train their own systems. If you just look around at the new agentive AI approaches, where actually small models win, and in combination, small models are, you know, more efficient and less costly than the big large ones, monolithic systems. But from my perspective, why I'm a believer in quantum is basically I see a potential that is not just in, you know, we have a new type of data with new kind of massive compression capabilities in quantum hardware, but also a totally new world for modeling and thinking about our data that opens up new research potential and insights that will change our algorithms and the way we think about the world and how we can model it and understand it. So this is the importance, I think. The classical will not go away, I guess. So in the long run, it will stay. And the data demand is not just AI driven, LLM driven. It's also, you know, the spread of these cloud services and distribution. You know, I was just thinking about our camera systems, our doorbells that record every movement in front of our house or apartment. You know, all that goes into these data centers, and this is sort of one of the big drivers for the high energy demand and large centers. You know, the LLMs might play a role, or AIs, but it will not be that important, my guess. You know, I was just yesterday, as I mentioned, I was in a computer store here that sells this new NVIDIA Spark device for $3,900 or something like that. And it has 1 petaflop capacity on a normal outlet in your household. You don't need any super power supply for it. And 1 petaflop is quite powerful, actually. You know, if you compare this to our supercomputer at IU, Indiana University has Big Red 200, which has just 6 petaflop. So with $24,000 and 6 of the NVIDIA devices, I can basically beat this supercomputer, you know. And this is sort of the development that we are facing, you know. So it's becoming cheaper hardware-wise and easier, less energy consumption. but the demand is spread in different domains, and this is the necessity for nuclear power plants to you know, power our cloud servers and compute centers.
Yeah, thanks, Damir. Ala, what's your perspective?
So I would like to extend what Damir said, and also refer to what he mentioned during his presentation, that LLMs are text-based, but actually in the real world we use words and things like that. But in the quantum world, it's even more true. That is to say, and especially if we think about quantum sensing, then the data is quantum in the first place. And so the idea would be to have, at least for those applications, for quantum chemistry in particular, physics-based models. So they are no longer large language, because it's not restricted to a language with text, and it's something different. And I think this is where there is a huge potential, but there's so much to. We are really at the starting point, and so this is where maybe analog quantum computing and digital quantum computing will join forces, and this is where we can have a virtuous loop. This is something I presented, I think, in this quantum AI series a couple of months ago. The idea of being able to simulate with the right mix of analog quantum computing and digital quantum computing, some physical system, and then to actually test it experimentally, and then look back and have like reinforcement learning, but for the whole thing, because we also have an IBM key player there, robots that can do experiments, you know, shake things, twirl, all that stuff, and so I think, yeah, at the moment it's like there are silos of expertise, and by combining some of them for practical use cases, could be some really exciting results in the short term. But it's also back to the pure LLM discussion. The IBM offering is more focused on enterprise, solving enterprise level challenges to combine with AI different silos, and we no longer have to deal with pure data silos, it's AI silos. And the open question is whether the large language model actually understand anything. And Yann Lequin, for example, Yann Lequin says, no, I mean, it's basically a parrot. So the key question is, and maybe this is where also with quantum-based artificial intelligence could help. Can we find ways of semantically making sense of different AI silos? So these are very exciting applications, which require only, I would say, a classic approach to focus on the right problem to solve, and to put together a multidisciplinary team. This is what IBM achieved with Cleveland Clinic and RIKEN. And then try and tackle a real world problem and deliver value. I think this is what it boils down to.
Yeah, thanks, Ala, for the point. And also, I would like to extend your point, because it was very beautiful about processing quantum data with quantum computers that maybe will be more efficient. Because as Ahmed said, we might need a quantum memory, but if the quantum memory has the same architecture as the quantum processor, then it will have the same coherence time, the same specs. Then it might be challenging to store it unless we make a hybrid quantum system, or we use different architectures together, where in some architecture the specs are much better for the coherence time, so the quantum data can live longer, and the quantum state can live longer, while the other processor performing some computations. But maybe that will be complicated, or might be achieved in the near future. So now I come to Shawi. I was coming to you about the first, if you have a comment, please, before I go to the question.
Oh, because you were just talking about coherence time. The fault of having a low coherence time could be used in a different context, because for noise modeling, for instance, things like that, it could be reframed. So having low coherence times for a quantum memory would be you know, a bad thing, but then like, you know, each qubit having a low coherence time could be used for as a noise, as a sensing type of application as well. So that was the comment. And the other thing was that for what Elaine was saying, Elaine, of the digital computing and the analog computing, there being a kind of battle, not a battle, but it's that digital information could be useful for digital products, like we have VR or, you know, virtual reality or simulations that are completely online, whereas applications for analog types of problems could be useful for analog type of solutions. So like things that have real world problem, if it doesn't become right, it's more that there needs to be some kind of hybrid approach, whereas like a fully digital simulation would be very useful in some kind of virtual world. So they will cover.
Yeah, that's a really great input, Shoei. So now I come to you about the quantum sensors regarding the energy consumption of the quantum algorithms and the quantum chips. Do you have a study or do you have an overview about the energy consumption of a quantum sensor comparing to classical ones, and what the cost to benefit ratio would matter in this, or not yet at the level of current available technology?
Yeah, that was there was a quantum sensing workshop earlier. There was this thing called Quantum World Congress. So there was these different companies that were trying to talk about like what was the efficiency of the resources needed for quantum sensing, but it really depends on the application. Say for example, someone gave the point of someone's using quantum sensing for seismic activity for volcanoes. The quantum sensing for the computational complexity for that kind of problem would be like it was a much larger computational complexity than potentially it would be a much larger computational complexity than our current existing classical devices that detect seismic activity. So this is something that is still being deployed and figured out whether that complexity is the same or if it's improved. But it would take a lot less resources, definitely. It's energy-wise, quantum sensing uses because it's just using extremely small sensing material. It would naturally require a lot less energy.
Yeah, that's clear. Thanks for your input. We have a question from Ziad. Using different quantum computing structures for memory will be also a hassle, as how would we transfer the quantum information? I think he means between different to the other quantum device from the quantum memory. So maybe I start with Ahmed to take his perspective on this. Yeah, you are muted, Ahmed.
Sorry, can you repeat the question again, please? I didn't.
So Ziad is making a comment and a question that using different quantum computing structures. So I was like discussing that maybe we use a hybrid architecture, we combine several technologies together. That for quantum memory, this will be a hassle, because how we are gonna transfer the quantum information to the other quantum device. So yeah, just an open question. I mean, there is no like definitive answer for it, but we would like to hear your perspective indeed.
Okay, it's all about the secret recipe that IBM is using to do the communications across different quantum system within quantum system 2, because we have the new concept of the tunable couplers, and we have different types. One type on the single quantum processor, so how we can let the qubits on the same chip can communicate in a distance, and we have the M couplers where we can communicate between multiple quantum processors on the same chip, and we have the L coupler, which is how we can let the different quantum systems to communicate together in a distance. Definitely, these are the design of these couplers. It's a secret how we do this, but it's in a simple terms, it's like a circuit, electric circuit, that it can amplify the signals, because these couplers and all this stuff we need to scale, because we have the problem of the crosstalk of the qubits. Okay, so if we have two qubits to each resides on the chip next to each other, one effect on the qubit, it might affect the other one, which will cause the crosstalk. So IBM is using the tunable couplers between these qubits to construct the frequency between these two. So which means we are making the noise or the signal or the effect is off between these two qubits. And when we need to do an operation with these two qubits, definitely we turn it on. So this is in a simple way how we can control this. Definitely in the modular systems, it's more complicated to apply even the gates, but there is a lot of techniques that we can do this, like the virtual gates, for example, and maybe in a different ways that we can move the swap gates using the swap gates effect to be able to do these effects or apply these gates across the different qubits on the same chip. It has pros and cons, we know, but at the end we need to reach to the fault tolerant quantum computer where we need a scalable system, and this is what we are trying to build right now. I hope I answered your question.
Yeah, thanks, Ahmed, for the clear and the nice answer. I'm going to now shift more to the definitions of the industry. So far we know, okay, that Turing machine limits. I mean, every computing architecture is expected to deliver certain computations with certain quality, and of course, the development of analog calculators was done, and that delivered a very nice computations. And now, until we move to the digital quantum digital computers, classical computers, and now we are in the quantum era, and we are moving from special purpose to more a universal quantum computer. So some people treat this as general purpose that in some contexts might give the illusion that the quantum will do everything. And some said, okay, no, the universal quantum computer will bring advantage to the use cases that's already will be useful for. So I can start with your perspective, Ahmed, and then I move to Ala and Damir and Shewi. So how do you see the universal quantum, the applications that will be called universal quantum computer or a general purpose quantum computer?
Still, the definition of the general purpose quantum computer is not standard. Let's say everyone is talking about the general purpose quantum computer from his perspective. For example, some people is saying, okay, now I'm developing different algorithms to solve some use cases. Yeah, for example, IBM, they are working across different industries, use cases, financial, industrial, energy, utility. So those are different use cases. We are trying to build algorithms and circuit, and these circuits we are running on IBM quantum hardware. Some can say, okay, this is a general purpose because we are building some solutions for a problem, we are running it on the same hardware. But the problem is some people, they are looking the other way around. They are looking into the classical computers that we are dealing with. You don't need to be an expert to do any task in your laptop, right? You don't know about the architecture of your processor. Is it Apple M1 or M4? Is it Intel? Is it Power? We don't care. I'm just running a program. I need to solve a problem. This problem I want to draw on Photoshop or provision a machine on a cloud, right? So this is another definition of quantum computer. I need to be isolated from the architecture that I'm working on as a developer. So I need to have multiple abstract layers to be able to encode my problem or use or have the problem, and I have a solution without worrying about the underlying technology. And in my point of view, we are still in the early stages. And if you look into the quantum computers, Richard Feynman, since 1981, when released, okay, I need a quantum computer. I need to build a quantum computer. It was just a theory. He wrote it in the book, right? After 45 years, we found there is a real quantum computer, a real machine. It took 45 years to develop one, almost 45 years, maybe, and more or less, right? So we're still in the early stage to compare the quantum machines and what it should be to the current classical maturity that we are dealing with. You have your mobile, it's a small computer, it's a small classical computer, right? We don't know what will come next into the quantum, but by all means, if you look into even IBM, if we look into what it's doing now, it's trying to put abstract layer on top of the quantum hardware. IBM in the roadmap, they are developing even the kernel, the Qiskit, runtime, and putting add-ons and Qiskit functions as well. So it's enabled the partners or the startups to build their own functions that it can accelerate in solving the problems. And if you look into this stacking, you will see we are going towards the general purpose to quantum computer. We are giving you ready-made functions that you can use it as part of your circuit to solve the problem. And I think we are going in the right path.
Okay, so that's great, and I think now that give a context about this. So I'm gonna move to Alain to take his perspective on the following. So what will be regarding the universality of quantum computing? What will be the use case that will prove that the quantum computing is actually surpassing the current available classical, super classical computers?
So I think there is a transition period. Ultimately, and we should also talk about software development lifecycle, SDLC, and IBM have very good business practices in that area. But we need to adapt that to the new quantum-centric supercomputing concept. So on SDLC, you start thinking about the end before you worry about how to put things together. You know, top down, not just bottom up. Okay, I think it's important. And now the other thing is so during that transition period, in order to demonstrate practical quantum advantage for a commercially relevant topic. In order to achieve that, I anticipate, I'm not the only one, that we might have to put together a commando team with the best experts in pure mathematics, quantum computing, the field of interest, which could be finance, or it could be other things. And at the expense of a properly layered approach, because we at first the aim would be to demonstrate, yes, that's it, and then with time we'll have time to the community will have time to re-architect the stuff. And also I think when you think about it, okay, I mean, I'm old enough to have witnessed the birth of the personal computer, right? I mean, and programming in assembly language on IBM and various mainframes as well and other things. But at the moment, it's fun for me because even though we use high-level languages like Python or C++ or Julia, we use higher languages, but the basic building blocks are really very close to the hardware. So the quantum circuit is actually a conceptualized model of underlying hardware, and eventually we need to be able to. So that's what could be achieved with Qiskit functions. We need to provide the end user developers with high level building blocks. And one of the big challenges if by doing so we are not going against the potential magic of quantum computing. Think about the teleportation algorithm. It's very simple. There are only 3 qubits. There are only a few, but it's very difficult, if not impossible, to visualize what happens because there is more than 3 dimensions. So that's, I think, one of the big unknowns, and maybe this is where AI could play a key role there, because AI could be trained to understand what the human mind cannot understand, because we have been the result of evolution for millions of years, and our brain, our is finally tuned to deal with the reality, and quantum is different. So I think that there are big challenge in software. Actually, I think the hardware it looks to be in a good shape, but I think people tend to be to overlook the challenge of designing a software that will really take advantage of these new quantum-centric supercomputing architectures, and beyond that, interconnected quantum nodes. I think the human brain will be the limit, the bottleneck, and so this is what I think. Anyway, thank you for your question.
Thanks a lot for your input. And now I'm coming to Damir. How do you see the quantum computing can help advancing the development of your LLM projects? And if yes, in what sense?
Advancing the development is a difficult question. You know, I mean, it's basically what we are doing is we are moving into a completely new world of thinking. You know, the classical digital world is basically we explored that, we know, and people try it with just exponentially grow the compute power, exponentially grow the amount of data, throw it into the models, and it will develop and improve. But it's actually, we see now that this doesn't work, and we have to get a paradigm shift. And this is why I was mentioning, for me, actually thinking about how I solve something in the quantum machine is a paradigm shift. It's thinking logically about a very different strategy or way how to model things, and think about solutions. And this is something that where I agree with Alain and Ahmed as well. Actually, we need actually new software systems. We need actually a new programming language. Qiskit is fantastic, but it's still embedded in this limited Python, and what we need is a new logic where we can express things that go beyond of this sort of thinking in what we have with Python, the world that it defines for us. There will be, new developments. People are coming up with ideas. I have a colleague here, Amr Sabri. He's working on programming languages for quantum. I believe, such people will come up with new strategies and ideas, how to improve that, and how to help us, as Alain mentioned, actually, how to help humans cope with this new kind of compute environment, where it's hard for us to think beyond just 3 or 4 dimensions, and now you're sort of in an unlimited dimensional space, so these are sort of the directions. For personally, for me, it's a new area, and everything is new, and this is what this research excitement is, basically. Students and colleagues get excited just about that, and we just want to explore new worlds. That's the thing. What it will bring us, this is a different question. We'll see in a decade or 2. So.
Yeah, thanks, Damir, for your answer. And now to show you, how do you benefit from Qiskit, or do you benefit from Qiskit and algorithms in Qiskit in the development of quantum sensors?
I mean, I benefited from Qiskit when I was learning about quantum computing and teaching it and making these labs so that people would understand things like QAOA and VQE and chemistry problems. And financial modeling problems, and it was really helpful in understanding that you have to do that this gate means this set of vector operations. So it was really helpful in learning about quantum computing. So it was helpful in learning about quantum computing, and it was familiar because it was Python, so everyone can understand it. But I think when I was like doing grad school in computer science, I looked up esoteric languages, which are like these weird other languages that never made it really, like that just got lost to research. But there's a lot of these kinds of other programming languages, like going along with the whole idea of building software for quantum computers, or even quantum sensing, which can be considered a type of quantum computer, or you know, it's all quantum devices. I don't even know what to say. It's quantum technology. It can be that people can make their own. There's actually a few. There's one language called entropy, which is a language that decays and as you code. So there's a lot of these kinds of interesting small research programming languages that are in academia, but they don't make it to industry. So that's one way to explore like software development and using that for more accurate modeling of quantum phenomena, so that like a universal quantum computer for some application. I don't think there's any universal quantum computer for everything, because like I think even the word quantum means small, so I don't think it probably wouldn't make sense to have some universal quantum computer for everything. But maybe sometimes people would be, especially in research, be looking to use some of these other, or be inspired by some of these other programming languages while they're already doing their software development in something like IBM's framework, or even if it's sensing, using some of these other kinds of programming language designs to have it accurately model what's happening in quantum sensing.
Yeah, thanks, Shoei, for your answer. So Ziad made a comment. I think I need to unpack it a bit. So the first, he was asking, isn't building a general purpose universal quantum computer going against the real purpose of quantum computing, as it originally has been developed as a model to simulate quantum systems? So I think this is why it was very beneficial to define the terminology in a way that's compatible with also, of course, the physics and everything, because I mean, when we define the general purpose or universal quantum computer, we mean, okay, maybe it's a device that will run all available quantum algorithms. So whatever we have a quantum algorithm is there on the shelf, the device, the quantum computing should run it to be universal. So it should run everything on the shelf. So the second point he makes is that about the mapping of problems, because now not all computations can be mapped on a unitary way of doing quantum computations, like the way that Schrödinger equation absorbs the evolution of quantum systems. So to map a non-unitary or a problem that's not compatible with the quantum physics would require to do very expensive transformation to make it work. So it's like if we wanted to have, for example, a certain division of numbers, if we cannot do it with unitary operators, it won't happen. So a workaround has to be established, and that might be very, very long path to achieve this. So to map these problems into quantum computers. This is why I think maybe later on in the near future, defining the universality of quantum computer, if we have a quantum algorithm that has been developed which obeys the laws of physics and also can satisfy the requirements, for example, like defense criteria and maybe others, then that will be universal because those are the ones that are available. So I would like to take your perspective on this. I'm going to start with Ahmed.
Yeah, thank you. This is a very good question, Ziad, and it shed the light on how we can get the benefits, the maximum benefits out of quantum computer and not make it like a waste of resources. And this is all connected because the sustainability is number one. You know, the energy, the energy consumption that the quantum computer is using, and all the question marks around it, which is, by the way, personally, I have a big question mark on the question itself, because comparing the quantum computing and the energy consumption right now, comparing to the supercomputers, I think, like Alan highlighted, the supercomputer, whilst idle, it might consume 10, maybe to 20 kilowatt, right? However, if you will compare it to a supercomputer, it's with megawatt, maybe 10, 20 megawatt. So the comparison is unfair, in my opinion, considering that the aim of quantum computer is accelerating the processing, right? So these 20 kilowatt of workload or energy consumption, it should resolve a problem in fraction of time, right? Comparing the supercomputer. So in my point of view, the quantum computer is more energy efficient than the supercomputers, if you will compare it apple to apple, okay? So definitely we need to be wise to select exactly what are the best problems that fits with the quantum computers, so it's not causing any energy loss or a waste of resources. So this is 100%, and we need definitely to have like a set of criteria to know exactly what are the problems that it's candidate to be resolved by quantum computers, or maybe in the classical computer as a supercomputer. And in my point of view, whatever problems that we are unable to resolve using a supercomputers, classical supercomputers, or the problems that has no or will take millions of years or thousands of years to be resolved using the classical computers, definitely it's a good candidate problem. These are the problems that will have a value to the humanity, so we'll start with these problems. So let's ask the right questions, and at the end, the quantum computer will not be able the only machine that it work to solve your problem or these problems. As we mentioned, the hybrid approach is the key for having a value out of the quantum computer. And as I mentioned, IBM is working now, and that has partnership. I think all of you know that IBM has partnership with AMD and the Cisco all together. So we have with AMD to have a supercomputer and running in the hybrid approach, and with Cisco and the network and quantum network and then telecommunications. So the ecosystem and the way that the quantum is working, when we ask the question, we shouldn't say, okay, the question is only about quantum computer, because quantum computers till the moment and in the future will not work alone. It will has QPU, quantum processing units, GPUs, and even CPUs, which is on the supercomputers. So this is when it comes into the general purpose on the way that we select the problems. We select the right problems, and we have to have a criteria to run these problems on the quantum computers. So I don't want to take much time on this. I hope that I made it clear what I'm thinking of, and this is my personal opinion, by the way.
Yeah, so Alain?
Yeah, so I would just say that this fits perfectly into what I said earlier, and that is we should think about software development lifecycle. And at the beginning, there is a need to think about what we are trying to achieve, okay, before rushing into putting bits and pieces of code together. And okay, so depending on the use case, again, I mean, if we take the huge challenge of improving the energy consumption for the Haber-Bosch process, there is a number of chemical reactions. Currently, it's beyond what can be simulated on the most powerful HPC. So that's one of the candidates for good use of, I would say, quantum-centric supercomputer. But the point is, once this problem is solved, it's only once. So it is okay to a certain extent, even if it costs a huge amount of energy, because the payback will be such, it's affordable, right? So that's one use case, very good one. But there are other use cases where the end user requires speed, and so we can think of a universal quantum-centric superconducting architecture and a generic software development SDLC cycle, but it would be on a use case by use case basis, and this is where consulting comes into play. Start with the end in mind, and prioritize action, and that requires involvement from just experts in quantum computing and other fields, but experts, I mean, people who put the money in the first place, or decide where to allocate the money, either more on AI or more on quantum plus AI, or you see. So back to the good old proven methods, software development lifecycle. And this is why it matters to have teams which combine their expertise, their experience, and together, yeah, that's what I would like to add. Okay.
Yeah, and Amir.
Yeah, I agree with Ahmed, actually. I think that, we spent, we were just stupid to do so, a long time, a whole semester trying to figure out how can we do nonlinearities in quantum computers, and playing around with quantum reservoir computing, with adding noise to saying, oh, it's actually, IBM should not go the direction to create coherent and error-free quantum qubits, because we need the noise as a nonlinearity function, for example, right? And this was basically, it's a waste of time going this direction, because we come from a perspective of how do we do AI and neural networks and so on in a classical environment, and don't think about how can we actually work with the quantum computers and use their advantage. And I believe that the direction, I can imagine that Qiskit, for example, will go into this direction to be a platform that does this automatically, that uses CPUs, GPUs, and QPUs, and figures out for you how to distribute the compute power automatically. This is the next direction, similar to what NVIDIA tries with Q.Q and so on. So everybody's thinking about the future will be this kind of heterogeneous hybrid platform, and we have to figure out ways how to make this sort of workable for humans and developers, engineers, and so on. So yeah, we should, this is what I'm saying, we should think in different ways when we are thinking about how can we use quantum in the best way.
Yeah. Thanks, Damir, for the point. I think I can extend a bit that, as you said, clearly this is, and also Ala and Ahmed, that's also the hurdle point, that we try to map every classical algorithm we know to quantum domain and the quantum realm, and then we pay the huge price with very heavy, expensive transformation methods to map from the classical to quantum, and we forget about the quantum nature itself. It should be linear, it's Hermitian, it's unitary, and all of these aspects. If we follow it, we might not need all of these expensive back and forth mapping between the classical and the quantum. So maybe in the future we should pay attention to developing native quantum algorithms in a new way, instead of mapping, as you said, the way that we do neural network and fitting to that. Of course, it will help that having platforms like Qiskit, which can decide which step to go where, either to do classical or GPU or QPU. But then maybe for the quantum part, native quantum algorithms can go. And this is what would bring us to the quantum sensing, since it's quantum anyway by itself. What's your perspective, Shoei, on this?
Oh, yeah, I just thought the point that Damir was making about reservoir computing was funny, because I did the same thing. I went through like the whole point of trying to like understand reservoir quantum computing with other physics PhDs, but then I realized like I don't really need to know that. That's more of a physics PhD program. And but the takeaway from that is I learned at least that I really don't need to know that, so that when I tell someone else about this, I can just say they're wasting their time. And that's probably the biggest takeaway of a lot of the entire quantum journey, is that there were things that big companies did earlier in the quantum phase that were kind of a waste of time, but then they just switched to a different way that made more sense. And then that's just how, that's how everyone learns and every industry grows, even with like AI being so in everyone's face now. You know, IBM was always like also ahead with like Watson and things like that. So it's useful to like just change to whatever makes sense with the time, that more and more applications and practical use cases come out. So I think like when there are practical use cases, when there's more out there of practical use cases, then naturally things will change.
Yeah, thanks, Shoei. I think we have all had very fruitful discussion. I mean, there always will be open questions that we might not really answer in one session or two. Of course, we are gonna in the upcoming sessions we are gonna discuss and address them. But maybe now it's a good moment to stop and, of course, reflect on this year by having wishes for to see very good quantum applications in the upcoming years. So I would like to thank you all for being present in the roundtable, and also for the speakers today, and for all of these nice discussions and very enlightening points. Thanks for Damir, and for Shoei, for Ala, and for Ahmed, for being here today, and looking forward to a meeting and also hosting you in the upcoming sessions as well.
Thank you all. Yeah.
Thank you. Thank you so much.
Thank you very much.
Yeah, thanks. Thank you.
Bye.
Wish you a new year. Bye-bye.
Bye.
Happy New Year. Bye-bye.